take a block that has 3 kilograms and we push it from rest. We push on it with a constant force, a distance of 3 meters. And then we stop pushing. And we find that that block, as a result, is moving at 20 meters per second. It then collides with a much larger block of 12 kilograms. And right after that block, there's a rough section of track that has a coefficient of kinetic friction of 0.2. Now, remember, we're always deciding, is this energy or is this momentum? The first part of the problem asks, what's that normal force by the hand on the block? How big is that force? Now, the decision tree is as follows. The first question we ask ourselves is this a collision? Well, yeah, it's going to collide in a minute, but it hasn't yet. Now, if it's a collision, that's a momentum problem. But it's not a collision. The second question we ask ourselves is time involved? Are we calculating time? Are we using time? If so, it's a momentum problem. But no, it's not time that's involved, it's distance. We're pushing for 3 meters. So if it's not one of those first two, it's likely an energy problem. And so I'm going to use energy. And to use energy, I always start with this equation here, energy initial. Let's put that down here. Energy initial is equal to energy final, except when it's not, and it's not when there's external variable. Now, the next step after I've written that equation is to identify what I mean by the initial state and the final state. Well, I'm trying to find out how hard this hand is pushing for the 3 meters. So I better put my initial at the beginning of those 3 meters and my final after those 3 meters. Now, at each of those events, I ask the same three questions. Right here, right at the start, is anything with mass moving? Not yet. Is anything up off the floor? No. Any springs stretched or compressed? No. So the energy initially is 0. Then I go to the final event and I ask, is anything with mass moving? Yes. So I have kinetic energy. Is anything up off the floor? No. Any springs stretched or compressed? No. Okay. Now I notice that this is not the same as that, and that's because the hand does positive var force times the distance. And so if I start plugging in what I know, the only unknown is the hand on the block. I multiply that by 3 meters and I get 1/2 times 3 kilograms times 20 meter per second squared. Now this means that the normal by the hand times 3 meters is equal to 600 joules, and that's going to give me the normal by the hand on the block is 200 newtons. Okay? See how easy that is? Then the little block slams into the big block, and we're told that after the collision, the little block stops. And the big block takes off. And the first thing I want to know is how fast is that big block going right after the collision? Well, that's, because it's a collision, that's a momentum problem. I conserve momentum, and I need a coordinate system with momentum. Now, before the collision, I had 3 kilograms moving at 20 meters per second to the right. That's positive momentum. I had 12 kilograms not moving at all. You see how I just wasted ink? After the collision, I had the 3 kilogram block not moving. I just wasted some more ink. And I had the 12 kilogram block moving, speed I don't know. But I know the direction it better be to the right. Okay? So this gives me 60 franci is equal to 12 kilograms V final, or V final is equal to a positive 5 meters per second. 5 meters per second to the right. Now, the next part of this question asks me, is this collision elastic, inelastic, or maximally inelastic? And I'm finding as I talk to people a lot of confusion about those three. Let's make a table here. Energy, you know, that marker's just about working. So, energy and momentum. So I've got an elastic collision, an inelastic collision, and a maximally inelastic. Now, for an elastic collision, is energy conserved? Mechanical energy, the type we've got formulas for, yes or no? Yes. Yes. Inelastic, it's not conserved. And maximally inelastic, it's not conserved. And they stick together. Now I know that after this collision, the little block is stopped and the big block's moving to the right at 5 meters per second. Can they be stuck together if they've got different velocities? No. And so that means it's got to be one of these two, elastic or inelastic. Now let's look at momentum. In an elastic collision, is momentum conserved, yes or no? Conserved. An inelastic collision, is momentum conserved or no? Conserved. In a maximally inelastic collision, conserved or no? Conserved. Conserved. Every collision. You cannot come up with a collision that does not conserve momentum. You cannot come up with a collision that will not conserve momentum. Now, folks, sometimes what we do here in physics is kind of wishy-washy. You know, we use frictionless tables and we use massless strings and we make approximations, you know, ignore the air resistance. In a collision, momentum is conserved, full stop. I don't mean if you assume that there's no air resistance or you assume a frictionless floor or, no, in real life, momentum is conserved, okay? Momentum is conserved, even if there's explosives involved, okay? It's always conserved. And that's why whenever we have a collision, we use momentum to solve that problem. Okay, so now, if I want to figure out what kind of collision this is, I have to figure out whether the energy is conserved. Well, before the collision, I have the little block moving at 20 meters per second, and that gives me 600 joules. After the collision, the little block stops and the big block is moving. It's got a mass of 12 kilograms and it's moving at 5 meters per second. And that's going to give me 150 joules. If those are different, if kinetic energy initial is not equal to kinetic energy final, then it's inelastic. There's not some test that you can just visually do to tell whether something is elastic or inelastic. You can tell if it's maximally elastic or not, but for the other two, you just have to do the calculation. Did the kinetic energy stay the same or did it not? Now, yes, question? No? Just waving your hand? Okay. Now, the next question on this problem asks, for how many seconds will block B, what's the friction force on the rough section of track? Well, finding a friction force we've known how to do for a long time. We draw a free body diagram. The weight force on that block is going to be 120 newtons. The normal force, therefore, is 120 newtons. That friction force is kinetic friction. That's going to be the mu sub k times the normal force. And that's going to give me 0.2 times 120 newtons, or 24 newtons. Now, this next part asks, how many seconds does the block scrape across that rough section? If I'm interested in seconds, in time, what kind of problem? Momentum. And so I use the, let me get myself some space here. It's not a collision anymore, it's a scraping. So I can't use momentum conservation. I have to use the general momentum equation, which is momentum initial is equal to momentum final, except when there's an impulse acting. So right as it starts scraping, I've got 12 kilograms moving at 5 meters per second, and then I've got a friction force of 24 newtons acting over some time, and I wait until it stops. And so that gives me 60 Franci minus 24 newtons. Delta T is equal to 0, or delta T is equal to 2.5 seconds.